Yes. Thank you, Ala. So in this second part, I will present the main results and discuss normal forms of geodesic vector fields. And then I will address the geodesic completeness problem and share some further results. Okay, so maybe first I will recall the what's the problem, okay? So what we have? So we have non-unimodular Lie algebras. They come in one parameter families and some discrete cases, okay? And then for each Lie algebra of them, let's say this is G, we have what's called the moduli space of left-invariant matrix. So we can take left-invariant matrix up to left-invariant matrix on G, which is sim star of G. So as recall that at the Lie algebra level, it's bilinearly symmetric forms which are non-degenerate. Okay, and the moduli space is given by taking these bilinear forms up to the action of the automorphism group of G. Okay. For each Lie algebra, we associate the moduli space, and this framework is maybe the best for people who are interested in the Ricci flow or curvature. But for us, we are interested in completeness and the dimension of isometry groups. So we can go one step further. We can take this up to scaling. So because these properties are invariants up to scaling. And this quotient, this projective quotient, is one-dimensional for this non-unimodular Lie algebras. It comes in one parameter families and some discrete orbits. So maybe I will try to draw maybe for one case. For example, let's say this is the pseudo-homothetic. For the pseudo-homothetic, this moduli space up to scaling has 4 discrete orbits and 2 one-parameter families. Okay, and what we do for each of these classes in the moduli space, we choose a preferred representative. This representative will be called normal form of left-invariant metric. So for each class, it's generically a 5-dimensional space of metrics, of left-invariant metrics, and we choose only one representative. And so our question is determining the special metrics in this moduli space, which is projectivized, in the sense that determine.
So do you distinguish Riemannian and pseudo-Riemannian, or do you fix the signature, or you consider everything?
Okay, so we don't fix the signature because for the isometries, it's like for the completeness, it's trivial, but for the isometries, it's not trivial. We don't know like which Riemannian metrics are of higher isometries or not. Okay, so yes. for the completeness, it's yes, it's in fact a trivial problem for Riemannian metrics. So we don't need to make this consideration. All left-invariant Riemannian metrics are complete since they have a definite first integral. But for the isometry problem, we need to make this consideration. So we take all the metrics, Riemannian and Lorentzian in our case of dimension 3. They can be Riemannian or Lorentzian, and we try to determine some special metrics which have higher dimensional isometry group, or they are complete. Because generically it's the opposite. Generically it's you have the isometry is only of dimension 3 and the metric is incomplete. So we try to find these special metrics. Okay, and the upcoming main result for this pseudo-homothetic Lie group is that we have only one complete metric with geodesic of bounded velocity, and we have a one parameter family of complete metrics with bounded velocity, but with no definite first integral. I will come back to this later. And moreover, we have another metric which is incomplete, but it's the only metric in this moduli space for this group which has a higher dimensional isometry group. Okay, and this is only an example. So for each, so the program consists to answer these questions for each point in this collection of moduli spaces up to scaling. Okay. So yeah, so this is what we said for the pseudo-homothetic group. So if we go back to the pseudo-homothetic Lie algebra, so is the Lie algebra given by this brackets relation. Okay, so E2 commutes with E3, and the add of E1 is written in this form. We have this Jordan block. Okay, so it's not diagonalizable over R. Okay, so I will come back. Okay, so we call P the Lie group of this Lie algebra, simply connected Lie group, and in this Lie group we have a one parameter family of left-invariant Lorentzian metrics which are complete and have bounded velocity. I will explain this later. And furthermore, up to automorphism and scaling, we have unique left-invariant Lorentzian metrics with geodesics of bounded velocity. Okay, so this is the one parameter family of left-invariant Lorentzian metric with bounded velocity. We have a special metric which is complete and of bounded velocity, and later I will come back to this metric which is special in the sense of isometries. It's the only metric which has extra isometries. Okay, and another result is that the set of complete metrics is not open and it's not closed for this group. So this is this provides an example, a counter example for the statement. Yeah, like if you say for the unimodular Lie groups, complete matrix is a closed subset of the moduli space. So this in the non-unimodular case provide a counter example where it's not open, neither open nor closed for complete matrix in the moduli space. Okay, I will come back to this very later. Okay. So in our preferred basis of brackets, which is I will recall it. It's E1, E2 is E2, E2, E3 is 0, E1, E3 is E2 plus E3. On this basis, on this preferred basis, the automorphism group of the pseudo-homothetic Lie algebra is given by this way. So for those who don't know, the automorphism group is the maps phi in GL of G that preserves the bracket. Okay, so we want the bracket of phi x, phi y to be phi of the bracket. Okay, and these maps consist of these matrices written in this basis. where I, B, C, D in R and C is not 0. Okay. And we can notice that this is 4-dimensional group, and it has 2 connected components. Okay. Okay. So I will recall again. So what we did. So we take the sim star. It consists of all bilinear maps which are symmetric and non-degenerate. This has dimension 6, and it's inside the vector space sim of G, so which is all symmetric bilinear maps. Okay, and what we do, we act by the automorphism group on this space, and we quotient up to scale. So doing that, we get one-dimensional set, and it's given by these representatives. So for each class, we choose our preferred representative, and we call it normal form. And we have these 2 one-parameter families, and we have 4 discrete orbits. So they are given by O3, O4, and later we have O5 and O6. Okay, so overall we have 2 one-parameter families and 4 discrete orbits. Okay, and these are all the metrics like Riemannian and Lorentzian up to the action of the automorphism group and scale. Okay, so what we do, we for each preferred representative of class of metrics in the moduli space, we write the geodesic equation for the corresponding metric to this. So it's again, it's homogeneous and quadratic equations. And if you see here, there is no way you can tell if it is complete or incomplete. Many equations are similar in writing. You see this one and this one, for example. But you cannot tell whenever it is complete or not without going through some analysis, which could be very complicated in some cases. Okay. For in this group, which is not always true, we have for each left-invariant matrix an invariant plane. So what's the meaning of invariance? Is that if you start by some initial condition in this plane, let's say this is some plane inside G of dimension 2. Okay, so if you start by an initial condition in this plane, the integral curve will not leave this plane. This is the meaning by invariant. So it's invariant by this geodesic vector field. Okay, this Euler-Arnold vector field. Okay, so here you can note that y0 is invariant, because if you take here y equals to 0, you see that the equation of y dot will be 0. This means that you are not the y coordinate will not variate locally, and it will stay 0. So y equals 0 will stay. If you start by initial condition in this plane, you'll stay inside this plane. Okay. And in this last column, we provide some first integrals. So maybe I will explain what is a first integral, and I will come back to this. Okay, so in our case, we have an ODE. So we say that some psi from R times omega in G is a first integral if the derivative, the total time derivative of psi t x of t is 0 for all solutions xt of the Euler-Arnold vector field, which is x dot equals fx. Okay. So for if you evaluate any solution, the derivative on time is 0. And what this means? This means that if the integral curves doesn't leave the level sets of this first integral. So if you take for example, I will give you an example. So a generic example is the energy. So if you take Q is the metric in question, so Qx of t, x of t, you evaluate on x of t and you take the derivative. We can show that this is 0. Okay, so I will show this in seconds. So this will give you 2 Qx dot of x, and you know from the Euler-Arnold equation that this x dot is at x of t dagger x of t. And by definition of the formal adjoints, we can we have this is equal Qx of t at x of t. We can remove this dagger if we move to the other side. Okay, this is by definition. And you know that at x, because the Jacobi, the Lie bracket is bilinear and alternating. So if you evaluate it at the same vector, you will get 0. Okay, and Qx with 0 is always 0. Okay. So Qx, this map, Qx x is always a first integral of the geodesic vector fields. So in the case where this is Riemannian, the level sets of these are spheres. So you go to the Lie algebra G and you draw the level sets of this Q. They will be some spheres of the given radius given by the level you are trying to draw. Okay, and it doesn't have negative levels, obviously, but the positive levels will give you spheres. They will foliate this G, and so being a first integral means that if you start by an initial condition here in this sphere, so it will be in some sphere at some level, so you will not leave this sphere. And since these Riemannian spheres are compact, this will imply the completeness of the geodesic vector. Okay. The case of Lorentzian matrix. So for this Qxx, the level sets will be of this form. So if it is 0, this will give you the cone. If it is negative, it will give you these two nubs. And if it is positive, it will be this one. Okay. And they also foliate everything. So these blue ones are the positive levels. Maybe I will draw by red here. So these are the negative levels. And the nil cone is the 0 level. Okay. So for each of these, if you start by an initial condition, let's say with positive energy, you will not leave this level. Okay. But as you see, this will not imply completeness because it's unbounded. Okay. This cannot imply completeness only if you have another first integral and you intersect with this level set. So because this is a first integral, this means that you don't get out of the level set. You have maybe another first integral, we say that it's phi. Its level sets maybe something like this. And you intersect with the energy level sets. If you get something bounded, this is a sufficient condition for completeness. Okay. So this is one of the techniques we can use for completeness. If we take two first integrals and we try to intersect them and get something bounded. Okay. So for this Lie group, every left invariant metric has some invariant plane. Also, other than the energy, we have outside the invariant plane a non-polynomial first integral, which will be useful in the proof of completeness in some cases, okay? Okay, so now we'll make the completeness study for this Lie group. So for the first family, so when R is positive, it's Riemannian, so it's complete. For R negative, I recall the expression of the metric. Okay, so for R negative, it's a Lorentzian metric, and the geodesic equation, the geodesic vector field have this idempotence, and as we said first, idempotence imply incompleteness. Okay, this means that if you evaluate this at the system, you get exactly this. Okay, so we will try to evaluate this for a simpler example. Okay. For example, 1, 0, 0 is an idempotent of 5. We'll check this. Okay, so for O5, if you evaluate 1, 0, 0, what you get? So for the first equation, you get 1 square plus 1 times 0, so it's 1. For the second equation, you get 0. For the last equation, as you have y and z, you will get also 0. So 1, 0, 0 maps to 1, 0, 0. So f of x0 equals x0. And this is the mean of having an idempotent, okay, for the vector field. Yeah. And as we showed, the existence of such idempotence imply the incompleteness. So for several metrics, we get this thing. So for O1R with R negative, for O2S with S negative, and for O5, they are incomplete metrics with idempotence. But as we are in the non-unimodular case, we get more incomplete metrics. Okay. So there are some incomplete metrics without idempotence. They all provide counterexample to Bromberg and Medina in the non-unimodular case. Okay. So okay. So for example, for O4, we notice that if we replace the equation of the zero level of the energy, this means that we are looking for integral null curves. So we get an equation of this form, which is x dot equals x squared plus z squared. Okay, so we know that this kind of equation is incomplete, but what about this kind of equation? What can we do? So we prove a lemma in dimension 1 differential equations in the case where we have a positive function here. So what we show that this is also incomplete, and it's even worse than the equation x dot equals ax squared. Okay, if we add some positive term, so it goes faster to infinity. Okay, I will show this. So okay, so for here for this case, we apply this lemma in for alpha equals z squared. So first we prove the lemma. So in the first part, we prove that an integral curve is not bounded. Okay, so we take a non-zero integral curve, and we suppose that it is bounded, I mean in a contradiction. So for example, gamma is between some m1 and some m2. Okay, and since the gamma dot is positive, so gamma is non-decreasing. Okay, so it's something like this between m1 and m2, and it must have two horizontal asymptotes. Okay, at m1 and m2. Okay, let's say that the limit at minus infinity is c1, and at plus infinity is c2. Okay, and this implies that the gamma dot at plus and minus infinity is 0. But what is gamma dot? Is gamma square plus alpha. But this alpha is positive, so it must be 0. And the limit of gamma at plus and minus infinity must be 0. So gamma is bounded between 0 and 0. So gamma is identically 0. Okay, and this contradicts the fact that we take a non-zero maximal curve. Okay, so for instance, gamma cannot be bounded. If we take a non-zero solution, it cannot be bounded. Okay, so let's suppose that it's not upper bounded. Okay, like we could have some lower bound, but we don't have an upper bound. Okay, so what we do, we compute the time for gamma to go from some initial condition x0 at the time t0 to plus infinity. Okay, so integrating the time form to compute the time, it's the integral of 1 dx over dt. So we make the change of variable, and so now we integrate from x0 to plus infinity, because here it's at x0 at t0, and we are computing the time until infinity. Okay, so replacing the equation of dx over dt, which is the x dot, it's ax squared plus alpha. We compare with the ax squared. We see that it needs less time to go to plus infinity than this one. Okay, and anyway, it goes to infinity in finite time, and this implies that it's an incomplete integral curve. Okay, so it's not defined until infinity, so it needs only finite time to reach the infinity. Okay, so this proves that we can generalize the typical equation x dot equals x squared to this case. Okay. Okay, this is for O4. Okay, for O6, it has an equation of this form, so it's directly incomplete. And now what's remaining is two cases. So we have O2S with S negative, which is this class of metrics, with S positive, and we have the metric O3, so which is this one. O2S and O3. Okay. So for these metrics, we make use of this non-polynomial first integrals. Okay, as we said, we try to intersect the level sets of this first integral and the energy level sets. and we prove that this intersection is bounded, and this will imply that the geodesic vector field is complete for this matrix. Okay, so first we try we start by the one parameter family O2S. Okay, we fix some S positive, and we denote QS the corresponding quadratic form given this way. Okay, we have that the plane y equals 0 is invariant, and it is a space-like plane, meaning that the restriction of the metric is Riemannian in this plane. And we pick any curve for an initial condition in this plane. We get an equation of this form. Okay, where sorry. Sorry, someone said something.
No, I think it's fine. You can continue.
Okay. Yeah. So S is positive, and having this equation means that x the points in y0 where this solution happen are of this form. So they are in some ellipse in the plane y0. So each integral curve must be in some ellipse of this form, which is compact. So it's complete. Okay. So if we start by any initial condition here, we'll stay here always. Okay, and we get this from the equation. Okay, replacing y by 0. So in the invariant plane y0, the geodesic vector field is complete. Okay, and you see it's the intersection of the space-like level sets with this plane, because this plane is space-like. Okay. So outside this plane, we'll make use of the non-polynomial first integral. So first, we observe that we can restrict ourselves to y positive. Since for y negative, we can make a corresponding geodesic using this involution. So we can restrict ourselves to y positive and prove whenever it's complete or not. Okay. So we use the other first integral. We take some level set of this first integral, let's say at level k, and the energy, and with this first integral. Okay. So we have some pictures. So like for the energy k, for example, k is positive, is something like this, and the y we suppose is positive. It's some locus here, and we use this level set, this first integral equal c. We get some surface like this. So what we are trying to prove is to show that the intersection is complete. Okay, is bounded. Okay. So from these equations, we derive the equation of y squared from the equation of the energy, and this implies that if y is bounded, then x and z will be bounded also. Okay, because if y is bounded, then this is x squared plus s z squared. It's like the equation of some ellipse. Okay. So we using the second equation, we derive the equation of z, and we replace it in the energy equation to have this. Okay. Now we have this tends to plus infinity when y tends to plus infinity. And since it's bounded, then we need to have y bounded, okay? Because if y is not bounded, this will go to plus infinity, which contradicts this fact that it is less than k, okay? And we conclude from y is bounded that x and z are also bounded, and so the intersection is some bounded curve, and this will imply that an integral curve will stay in this bounded curve, so it must be complete. Okay. So for O3 we do exactly the same, but here the difference is that in the invariant plane, the geodesic vector field is unbounded. So you see here the solution is exponential, so it's unbounded. For the other one, all the solutions were bounded. So this make this complete metric special. But for the study, it's exactly through the same method. Okay, we use both first integrals to prove that the intersection is bounded in Z positive. And for this special metric, we did some dynamical study. So, for instance, the singularities of this vector field, the corresponding vector field of O3, are omega 1, omega 2, and omega 3. It has three singularities that span the vector space, and the eigenvalues of the linearized vector field at each singularity provides some key informations about the geodesic vector field. So here I will give you some example. So if we take the singularity omega 3 and we compute the eigenvalues of the differential, we will get two purely imaginary eigenvalues with zero eigenvalue, and these purely imaginary eigenvalues cause some elliptic behavior, as here in the picture. So this line in black, it shows the singular line corresponding to the singularity W3, and the geodesic vector fields rotate around this singularity, which is the elliptic behavior we are talking about for the linearized vector field. And the direction of rotation depends on the sign of Z, okay? Because you see as this Z0 is the invariant plane, Z equals 0, and Z positive is one invariant locus, and Z negative is another invariant locus. And for each locus, we have this invariance behavior. Maybe this picture shows better. Yeah, because it's pointed with this singularity. Okay. So now I will come back on to the result of non-closedness of the set of complete metrics. So from the works of Bromberg, Medina, and Shafi'i, Ferreira, and Reis, we know that the set of complete metrics is closed for unimodular Lie groups. So the aim is to show that our Lie group provides a counterexample to this. So for R different from 0, this matrix is in the class of O and R. Okay, so acting by the automorphism group and scaling, we can go from this to this one. Okay, So they lie in the same class. Remember that each class has 5-dimensional set of possible representative, and this representative we choose, it's the normal form. Okay. So we take a sequence of these representatives. It converges to O3, the metric O3. So we have a sequence of representatives in O1R, which tends to O3. But O1R are can be either complete or incomplete, depending on whenever R is positive or negative. But O3 is complete. Okay, so it is. So it is not open because the set of incomplete matrix is not closed, and we do another sequence to prove that it is not closed. Okay, of representatives, because the O2S matrix for S positives are complete matrix, and they converge to this incomplete matrix. Okay, and so it's neither open nor closed. Okay, maybe at the end I will yeah. So some further results is that the metric O6, which is an incomplete metric. So I will go back to 6. Yeah, so this metric. Okay, this is an incomplete metric because it has this equation. However, for the isometry group, we show that it is flat, and it's the only metric with constant sectional curvature. And for its isometry group, we show in another upcoming paper that it is the only one which has 4-dimensional isometry group. So it's the only one with extra symmetry. So overall, we have one parameter family of complete metrics. We have incomplete metrics coming in one parameter families and in single and in single orbits, and we have a special complete metric and also a special metric with 4-dimensional isometry. So the black ones are the special metrics, and the other ones are the generic metrics, which are incomplete and having isometry group of dimension 3. Okay. So the classification is more interesting in the case of affine plus R times R, which is one of the hyperbolic algebras we stated in the beginning. So they are of the form A1, A2 is A2, A1, E3 is lambda E3, and E2 commutes with E3. This is the case where this lambda equals 0. So what we do, we make the complete classification as follows. So we make the classification using the derived and center. So E3 commutes with everyone in the case where lambda equals 0. So it's central, and the derived Lie subalgebra is given by the span of E2 in this case. Okay, so we note this D and we note this by Z. And so a metric, a left-invariant metric is incomplete on this group if and only if we either have idempotent, but we have more, as we said, that having idempotent is the case of Bromberg and Medina. So we have more class. It's the case where the center is like and not Q orthogonal to the derived. We showed that these metrics are incomplete. Moreover, if the center is like but Q orthogonal to the derived, then the left-invariant metric in question is complete, but with unbounded velocity. And we have, in fact, only one representative of this one, okay? And the last case is that if the geodesic field have no idempotent and Z is not like, in this case, it turns out that Z, the center is time-like, and it provides, so it's time-like, and since the center is always Killing field, it provides another first integral given by its the square of the corresponding one form to the center. And so we can build a quadratic definite first integral, and for this case the geodesic vector field is bounded and it's obviously complete, and this contain many classes. However, for the case of lambda different from 0, we get exactly the same thing as the pseudo-homothetic group. So we get one complete metric with unbounded velocity, and all the others are with bounded velocity, but without having first integral. The difference is that the equation are much complicated, and we have more normal forms. So we have more classes. We have 2 that comes in 1 parameter families, and overall we have 12 classes of normal forms. Okay. And yeah, if you remember, it remains the 1 parameter family given by the elliptic algebras. So the algebras where the bracket is sorry. Where the bracket is E1, E2, or I write it directly. So E2 commutes with E3, and the add of E1 is this matrix for some theta different from pi over 2, because we exclude the unimodular case. As we said, Guideri proves that in the case where theta equals pi over 2, that it is complete with all left-invariant metrics complete, and theta is 0 pi. Okay, for these groups, what is interesting, so you see, usually we use idempotents and we use quadratic first integrals. For these Lie groups, we don't have idempotent for every left-invariant metric. There is no idempotent. Also, there is no quadratic first integral. Okay. So this list of groups is the most complicated. So all the usual methods does not work for this list of Lie groups. Okay. Yeah, and this completes the talk. So thank you for your attention.